Hey geometry. Sorry, I'm turning music off. Lesson 3, scaling principle for area. So first of all, we talked about area. We talked about area with irrational numbers. Then we talked about area and sort of adding area together and subtracting area away depending on what the figure is and if there are any overlays or cutouts. Now we're going to talk about scaling and area. So we're going to determine the area of similar figures and similar parallelograms and then compare the scale factor of the similarity transformation to the value of the ratio of the area of the image to the area of the pre-image. Okay, so we have some vocabulary words that we haven't used in a while that you're going to have to remember: pre-image, image, scale factor, etc. The goal here is for you to see that areas of similar figures are related by the square of the scale factor. Okay, so let's go ahead and work through an exploratory challenge, and then we'll skim through some exercises until you understand things. So first of all, we're going to complete parts 1 through 3, I through I, of the table for each of the figures in questions A through D. So determine the area of the figure of the pre-image, that's I, determine the scaled dimensions of the figure based on the provided scale factor, and then I, determine the area of the dilated figure. Then answer the questions that follow. Okay, so I'm going to go ahead and skim ahead because I cut each picture to be with each part of the table. So first of all, if we look at the area of the original figure, I have area equals 1/2 base times height. So 8 times 3 is 24, half of that is 12. I've got a scale factor of 3. So the dimensions of a similar figure would be 24 and 9. So area, I guess I could write here, 24 by 9. The area of a similar figure would be 1/2 times base times height. Calculator. 24 times 9. Half that is 40. 24 times 9 divided by 2. 108. And then the ratio of the similar area to the original area. So I've got 108 over 12 equals 9. Okay, so write that down because we're going to compare this at the end, right? Next one, I have area of the original figure, 1/2 times base times height. 5 times 3 is 15, half of that is 7.5. If I scale it by 2, I get 10 by 6. Area of the new one would be 1/2 times 10 times 6. Half of 60 is 30. And then we have the scaled over the original, and that gives me 4. So we're looking for a pattern here. Area of the original figure. For this figure, we just do base times height. It's almost like it's 2 triangles, so we don't have to half it. Area equals base times height, or length, well, base times height. So that gives me 5 times 4, which is 20. If I'm halving that, that means my new dimensions are 2.5 by 2. Area is 2.5 times 2, which would give me 5. Similar area over original is 1/4. So if you try to see a pattern there. Last one. Area of original is 2 times 3. Okay, scale it by 3 halves, and my new dimensions are going to be 3 times 3 halves, which is 9/2, 4.5. And then 3 halves times 2 is 3. Area of this is going to be 9, 10, 11, 12, 13 and a half. Yep. I don't know why I question myself sometimes. That was an easy one. And then similar area over original area is 9/4. Do you see a pattern yet? You have them all written down on the same piece of paper for yours. So I'm wondering if you see a pattern. So make a conjecture or a guess about the relationship between the areas of the original figure and the similar figure with respect to the scale factor between the figures. If you look at the scale factor and compare it to the ratio of, the area of the similar figure over the area of the original figure, it looks like we are squaring the scale factor, right? Pretty cool. So it seems as though the value of the ratio of the area of the similar figure to the area of the original figure is the square of the scale factor of the dilation. That's my conjecture. So discuss for a second. So we guessed that the relationship between the area of a figure and the area of a figure similar to it is the square of the scale factor, right? If we look here at polygon Q, it's the image of polygon P with a scale factor of R. So it's a dilation, scale factor equals R. Okay, how can we show that our conjecture holds for a polygon like this? Like, what? This is so many different shapes. I wouldn't even know what to do. Polygon Q is the image of P under a similarity transformation of R. The way that you would tackle a problem like this is we find the area of each of them and compare it. So we find the area of each and compare the areas of the two figures. We would find, we would look at the area of the similar over the area of the original, and I would assume that the difference or the ratio would be the scale factor squared. But how do we compute the area of a polygon like this? Let's see if I can, I can't. I was going to try to make that bigger. Really, the way that we would do this, let me get a different pen, is we'd have to break it up into triangles, which is like crazy, but it works. So we find the area, we break the polygon up into triangles, and it'd have to be non-overlapping triangles. So we would just look at it. I don't know if that one works. It looks like it might. So I got 3 triangles. And we compare really the area of each parts of the triangles. Sorry. I'm not sure I like that one. I just don't know if those pieces and parts match. So I have a triangle. If I break that one up, I'm just going to go from here to here, because I know those would be triangles. We can do that again here. But I'm not sure about these, so let's just connect those dots. And then I have this one in the middle. So 1, 2, 3, 4, 5 triangles. So subdividing similar polygons into non-overlapping triangles, which I can do the exact same for here. It's going to look a little bit messier because it's smaller, and my drawing abilities on this iPad are not awesome, right? All right. So let me write something down and I'll be right back. The scaling principle for triangles. Why don't you go ahead and fill this in. So if similar triangles S and T are related by a scale factor of R, then the respective areas are related by a factor of R squared. Okay, we're going to come back to this one in a little bit. Okay, not quite yet. So here I just drew two similar triangles. We're just going to talk about the scaling principle for triangles. So I have triangle S and triangle T, and I drew a base and height on triangle S. Triangle T has been scaled by a factor of R. So I have R times H and R times S. If I look at the area of triangle S, I have, let's see, the area, let's do area of triangle S, 1/2 base times height. And if I look at the area of triangle T, I have 1/2, ooh, I see an error, R times B. 1/2 base, which is RB, and height, which is RH. I'm going to collect like terms, which gives me 1/2 R squared times base times height. Right? So there is my scale factor squared. Okay? Now if I take it a step further, like we did in the first example, if I compare the area of the scaled to the area of the original, I get 1/2 R squared BH over 1/2 BH. I can simplify, and I'm left with R squared. It's like magic. So we just proved the scaling factor, or sorry, the scaling principle for triangles, right? All right. Okay, how about the scaling principle for polygons? If similar polygons P and Q are related by a scale factor of R, then their respective areas are related by a factor of R squared. Okay, and we're going to look at those two polygons from the beginning to prove this fact. So here we have polygon P and Q, just like the previous example, the previous slide, and we've sectioned it out into triangles, just like I tried to draw with my little cool highlighter. So if I look at triangle P, this is the triangle before we scaled it. So I've got lots of, this is the polygon before I scaled it. I have lots of triangles in here. Triangle 1, triangle 2, triangle 3, 4, and 5. So the area of the polygon P is going to be the area of triangle 1 plus triangle 2, 3, 4, and 5. Okay, those are where T is the area of the triangle, of each triangle. So that's the area of the whole polygon. I added all those together. Now we scaled to get to polygon Q. So if we remember, we already did the scaling principle for triangles. So it's R squared times the area of triangle 1. R squared times the area of triangle 2. R squared triangle 3. R squared times the area of triangle 4, etc. So if I look at the area of polygon Q, it's going to be all this added up. R squared T1, R squared T2, r squared t3, r squared t4, and r squared t5. I can factor out an r squared, and I've got t1, t2, t3, t4, and t5. Now if I do the same thing as the previous example, I'm going to do the area of the scaled polygon over the area of the original, which gives me r squared, writing a lot, over the area of the original polygon, which, as you can see, I can simplify my fraction, and all I'm going to have left is r squared. We just proved the scaling principle for polygons. Awesome? Awesome. Let's try to put it into practice. So I have rectangles A and B. They are similar and are drawn to scale. If the area of triangle A is 88 millimeters squared, what is the area of rectangle B? Okay, so we need to figure out the scale factor. The scale factor is going to be the length, 30 over 16, which I can simplify. So there's my scale factor. My area scale factor is going to be 1.875 squared. So the area of B is 1.875 times the area of A. So I can easily say that it's 1.875, I forgot to put my squared in, times 88. Or, crunch the number, 1.875 squared times 88. 309.375 millimeters squared. So we had to find our scale factor, square it, and multiply it times the original area to get the area of the new. Figures E and F are similar and drawn to scale. The area of figure E is 120 millimeters squared. What is the area of figure F? So here we're getting smaller, right? So I need to look at my scale factor. So my scale factor is going to be less than 1. It's going to be small length over big length. Simplify, 0.625. So my area of figure F is 0.625 squared times my area of figure A, or E. So area of F is 0.625 squared times 120. Let's see what it does. 0.625 squared times 120. I got 46.875 millimeters squared. Pretty simple? Cool. The scaling principle for area. If similar figures A and B are related by a scale factor of R, then their respective areas are related by a factor of R squared. And that's it. Those are the 3 things that we did today. Sort of fun, so we can check it out with our problem set. But basically, when you have a scale factor and you're doing area, the area is related by your scale factor squared. And that holds true for any area because we have units squared. That's how I always remembered it. Good job.